Dear listeners, you are once again welcome to this lecture. And in today's lecture should be a continuation of the last one, where we talk about finite sets, countably infinite sets, and the countable sets. Now, recall that given a set X, the cardinality of X abbreviated card X stands for the number of elements. Recall also that if cardinality of X is equal to 0, or cardinality of X is equal to n naught for some n naught in the set of natural numbers, then X is called a finite set. Recall also that X is called a countably infinite set if and only if there exists a one-to-one onto function from or vice versa. So a countably infinite set is a set that there is possibility of establishing a one-to-one correspondence between the set and the set of natural numbers. Remember that one-to-one correspondence between two sets means that we have a one-to-one function that is also onto. That is to say that the function is a bijective map. Once we're able to establish a bijective map between the set of natural numbers and the set X, then that set X should be called a countably infinite set. If the set X is said to be countable if and only if X is either finite or countably infinite. So a countable set is a set that is either finite or countably infinite. Remember that countably infinite sets are also called denumerable sets. Countably infinite sets are also called denumerable sets. A countably infinite set is also called a denumerable set. So a set is countable if it is either finite or denumerable. Meaning that every finite set is countable. Every countably infinite set is countable, but not the other way around, in the sense that when you tell somebody to define a countable set, that person will say or if you tell somebody to define a countable set, the person says a finite set. Or you tell the person to define a finite set, he says a countable, he or she says a countable set. This should not create confusion if we really follow this lecture completely. So for us to talk about a countable set is a set that is either a finite set or the numerable set. So once one gets that a set is finite, then that set is countable. If one gets that a set is countably infinite or the numerable, then that particular set is also countable. Now, to start today's lecture, what I've just done is to try to recall what we did in the previous lecture. But for today's lecture, the following facts should be noted. I will put them down, but will not prove them. One of them is that a subset of, if you have a countably infinite set, any subset of it is either finite or countably infinite. A subset of a countably infinite set is either finite or countably infinite. Another point we should note is that every subset of a countable set is countable. Then the next one, which is very important in what follows, is the following, that countable union of countable sets is countable. To throw more light on this last one, so that people will appreciate what we mean by countable union of the countable sets being countable. I recall that if we are given the collection of sets, say E1, E2, maybe we are giving this as a collection of sets E1, E2, E3, and so on and so forth. This is a collection of sets, a family of sets E1, E2, E3, and so on. And you will see that this is a countable collection of sets because this collection is denumerable in the sense that if I now have the set of natural numbers 1, 2, 3, and so on, then we can establish a one-to-one correspondence between the set of natural numbers and this family of sets, in the sense that we've gotten a function f that say maps E1 to 1, or maps 1 to E1, and so on and so forth. So in this particular case, we are talking about a certain function f that maps n to En. And this is happening for any n in the set of natural numbers. So what this means is that this family is a countable collection of sets. Now, this countable collection of sets, if each En is countable, then this particular collection will be called a countable collection of countable sets. So what we are saying is that if this collection is made up of countable sets, then the union n equals 1 to infinity of En as a set, if I call it E equals union n equals 1 to infinity of En will turn out to be a countable set. So that is what this statement is saying. Now, for us to see why this is important, if you look at the set of real numbers, say, if we take R, the set of real numbers, and I take X in the set of real numbers, X as a point, you will observe that the singleton X, that is this 1 point set, is a countable set. It is a countable set because its cardinality is 1, meaning that it's finite, and every finite set is countable. But if I look at the union over x in the set of real numbers of these singletons x, this is a union of countable sets, but it is not a countable union. Reason being that the set of real numbers is not countable. I will at this juncture request the listeners to prove that the set of real numbers is not countable. That is to say, they should show that we cannot find a one-to-one map between the set of real numbers and the set of natural numbers. So this is an uncountable union of countable sets, and this particular union turns out to be the entire real line. What this means is that this union, though is a union of countable sets, it turns out to be what? Not countable. It's not countable. But whenever we take a union of a countable union of countable sets, then that countable union of countable sets must be what? Countable by this let me call it proposition. Now, the next thing I would like us to know is the following. Remember that before we got into talking about this countability of sets, we talked about one-to-one onto function. Now, this leads me to the following proposition, and I would like us to start following attentively from now on. Look at this following proposition. What does the proposition say? Given 3 sets, give it 3 non-empty sets. Suppose these 2 functions are one-to-one and onto. Then our conclusion should be that the composition G composed by F, the composition of these 2 functions is also 1-to-1 and onto. For us to really see this, look at this is the set X, and here is the set Y. We now have the set Z. F is a map from X to Y, and G is a map from Y to Z. So the map G composed by F is a map from X to Z that which are denoted by G of G composed by F. This by definition means that for any X we pick in X, G composed by F of X is nothing but G acting on F of X. So that is the composition. That is what the composition is all about. And we know this from elementary mathematics. So what we are saying is that once F is one-to-one and onto, and G is one-to-one and onto, then this composition will also be one-to-one and onto. Now, to see that, proof of this follows as I'll present. Now, we are given that F is one-to-one and onto, and we are given that G is one-to-one and onto. Let me first of all treat the case where F and G are one-to-one. Now, F being one-to-one implies that X, Y in X not equal to Y implies F of X is not equal to F of Y. Remember, a one-to-one map is a map that maps distinct elements to distinct images. G being one-to-one also implies that given u v in y, u not equal to v implies implies g of u is not equal to g of v. Now, from this, we therefore have that for any x, y in x, x not equal to y implies that f of x is not equal to f of y. This implies that, please, before I explain further, let us note that I'm working on an assumption that x is the domain of f. The entire x is the domain of f, and the entire y is the domain of g. The essence of this is for g to be able to act on f of y, so that this will be the entire, meaning that g has the capacity of picking any element in y. So the domain is not restricted. That is the assumption. Otherwise, if we want to be more technical, I'll be taking x and y from domain of f. And I will require that the range of f and the domain of g must intersect, or rather that the domain of, that the range of f must be a subset of the domain of g. But for now, for simplicity, let us assume that the domain of f is the entire x, and the domain of g is the entire y. So now, from what we are doing, since f is 1 to 1, x not equal to y implies that f of x is not equal to f of y, and f of x not equal to f of y will in turn imply that what, that g of f of x is not equal to g of f of y. And this implies, therefore, that g composed by f of x is not equal to g composed by f of y. So what we've got is, therefore, that x not equal to y implies g composed by f of x is not equal to g composed by f of y. Thus, g composed by f is 1 to 1. Is 1 to 1. So this we've seen that whenever two functions as established above are both 1 to 1, then their composition will turn out to be 1 to 1. Now, the other one is if we look at the two functions being onto. The two functions being onto means that for f, it means that since g is onto, we have that for any z we take in z, in capital Z, there exists y depending on z in capital Y, such that g of y sub z is equal to z. This is what we recall is the definition of a map being onto. Also, since f is onto, we obtain that for any y we pick in y, there exists x depending on y in x, such that f of x of y is equal to y. Is equal to y. So, from these, we obtain in particular that for yz in y, for this yz, for this particular yz in y, since for any y we pick in y, we can find xy in x, sorry, that this holds. It means that since this yz in y, we can also find a corresponding x in x. So for this yz in y, there exists what I'll call xz, which is defined as x sub yz in x, such that f of xz will be equal to yz. This is because f is onto. This means, therefore, g of f of xz will be equal to g of yz, which is equal to z, considering what we got here and what we got here. So, what this means is therefore, what we can conclude from here is that for any z we pick in the set z, there exists xz in x such that g composed by f of xz is equal to g of f of xz, and this is equal to g of yz, which is equal to z. So what we've gotten in actual sense is that what this means is that for any z I pick in capital Z, there exists xz in x such that g composed by f of xz is equal to z. So what this means, what we've gotten therefore is that the function g composed by f is onto. So whenever f and g are onto maps regarding our scenario above, once f and g are onto map, then their composition is also an onto map. What's the essence of bringing up this? The reason why I decided to bring this up is the following. If we are given a set x, say, and we have that x is countable. If I'm given a set x is not necessarily the set of natural numbers, and we have that this set x is countable. If there is another set y, and I'm able to establish that there is a one-to-one correspondence between that I'm able to get a map H from x to y, which is one-to-one, and onto map or onto function, then this is enough. Being able to establish this existence of a one-to-one correspondence between x and y is enough for me to conclude that y is also countable. The reason is because since we know that x is countable, then there is a one-to-one correspondence, call it f, between the set of natural numbers and x. This f is one-to-one and onto. And since x is, since h is a one-to-one and onto map from x to y, then the composition of h and f by the what we've established above will give us a one-to-one onto map from the set of natural numbers to y. And this means that we've established a one-to-one correspondence between the set of natural numbers and y. And hence, y is countable. So this particular thing, what I pointed out now, will help us in what I want to establish. And what I really want to establish, my target in this lecture is to get the following. Target is to get that Q, the set of rational numbers, is countable. This is what I would like to establish now. So how do I do this? To be able to do this, let us go as follows. I will do the following construction. Given n in the set of natural numbers, I want us to define a set En to be equal to the collection of all m over n so that m is an integer. The collection of all m over n so that m is an integer. That's the construction I've done, or rather I've made. So what we shall do now is to see if we can check that for each n in the set of natural numbers, that En is countable. If I get that En is countable, it means that each set En is a countable set. Meaning that if I take the union n equals 1 to infinity of En, I've gotten a countable union of a countable union of countable sets. And by what I pointed out above, this countable union of countable sets will be countable. Then the next thing we should establish is to establish that this union is actually equal to Q, the set of rational numbers. When this is established, it means that Q is a countable union of countable sets, and therefore countable. That is the idea behind what I'll do in this square. So let us try to do that. Now, I will do the following claims. Claims. Number one, for any n in the set of natural numbers, En is countable. Number two, Q, the set of rational numbers, is equal to union n equals 1 to infinity of En. So we'll try to establish these two claims. Let us start with the first one, proof of claims. Proof of claim number one. I would like us to recall that I want us to recall that En, okay, it's still close, so there's no cause for alarm. Recall that En is defined as given above. So we want to show that for each n in the set of natural numbers, En is countable. But to me, I think this is somehow trivial because we should observe that for any n in the set of natural numbers, for any n in the set of natural numbers, if we define a map, say f sub n, from En to Z, the set of integers, or rather, let me say, okay, it's okay, there's no problem. If I define Fn from En to the set of integers by define this by Fn of m over n equals m. Remember that typical element of En is m over n. So what this function does is that it will take m over n back to m. Then, that is, if we define for any n in the set of natural numbers, let us define the map f sub n from E sub n to the set of integers by Fn of m over n equals m. Then Fn is 1 to 1 and onto. This is given xn and yn in En. Please, let us know this. I'm indexing x by n because En, as n is varying, En is varying. So I'm trying to take them collectively so that we'll get it done at the same time. Because nothing stops me from taking E1 first and show that E1 is countable. In that particular case, I'll take X1, Y1 in E1. Then do what I want to do. The next thing is what? I'll take E2 and so on. So this dependence of Xn, X on n, Y on n is because of the fact that as n is varying in the set of natural numbers, En will be varying. So if we take Xn, Yn in En, such that Xn is not equal to Yn, we show that Fn of Sn is not equal to Fn of Yn. Once we're able to establish this, it means that for each n in the set of natural numbers, Fn is 1 to 1 because distinct elements will have distinct images. Now, let us note the following. Note that Xn, Sn, Yn in En implies that there exists, say, M1, M2 in the set of integers so that Sn is equal to M1 over n and Yn is equal to M2 over n. This is because of how the elements of En are. Let me recall here that for each n in the set of natural numbers, En is equal to m over n, so that m is in the set of integers. So if we take xn and yn in En, what it means is that we can find two integers, m1 and m2, so that Sn is equal to m1 over n, and yn will be m2 over n. What this therefore gives is that, therefore, Sn not equal to yn implies that m1 over n is not equal to m2 over n. And this implies that m1 is not equal to what? m2. m1 is not equal to m2. But by our definition of Fn, this will in turn imply that Fn of m1 over n, sorry, let me try to make it as clear as possible. Let me say, but Fn of Sn is equal to Fn of m1 over n, and this is equal to m1. And Fn of yn is equal to Fn of m2 over n, and this is equal to m2. Therefore, m1 not equal to m2 implies that Fn of m1 over n is not equal to Fn of m2 over n. And this implies that m1 is not equal, sorry, and this implies that Fn of Sn is not equal to Fn of Yn. So what we've gotten is therefore that m1, therefore what we've gotten is that Sn not equal to Yn implies that Fn of Sn is not equal to Fn of Yn. So Fn is 1 to 1. To check that Fn, so for any n in the set of natural numbers, Fn from En to Z is 1 to 1. Now, to check that Fn is onto, I think that one is trivial. Next, that for any n in the set of natural numbers, Fn is onto follows from the fact that for any m I pick in Z, the set of integers, there exists m over n in the set En such that Fn of m over n is equal to m. So this being onto is trivial. This means therefore that Fn from En to Z is onto. So what have we established? What we've established is that Fn is one-to-one and onto. And for this reason, we can conclude that for each n, En is countable because we've established a one-to-one onto correspondence between En and the what? And the Z. And the countability of En follows from what I explained earlier, that since Z is countable, there is a one-to-one correspondence between Z and the set of natural numbers. So the composition of this map and that particular one-to-one correspondence between Z and the set of natural numbers will give us what we are looking for. In fact, we've established a one-to-one correspondence between En and Z, but I've not really put forth that Z is countable. Now, the countability, we must note that Z, the set of integers, is countable. The set of integers is countable. To see this, I want us to observe that Z, as we know, is nothing but the set, say, -3, -2, -1, 0, 1, 2, 3, and so on. And this I can rearrange because in set theory, a rearrangement of elements in the set does not distort the meaning of what the set stands for. So this is equal to, I can rearrange by saying that this is equal to 0, -1, 1, -2, 2, -3, 3, and so on. Now with this, if I now put down n here, if I now put down the set of natural numbers here, and we know that the set of natural numbers is the set 1, 2, 3, 4, 5, and so on. Then with this arrangement, we can do the following. We have that 0 is mapped to 1 or 1 is mapped to 0. This what I'm doing right now pictorially establishes a one-to-one correspondence between the set of natural numbers and the set of integers. And therefore, the set of integers is countable. To see this clearly, this particular scenario I've painted here can be depicted as follows. The following map captures what I'm talking about here. If we define, say we define f from the set of natural numbers to the set of integers by define this map for any n in the set of natural numbers by the following formula. How is defined is the following. I'll look at f of n to be equal to, say, n minus 1 over 2 if n is odd. Or I will define it as minus n over 2 if n is even. If I define this map, you'll find out that this particular map actually follows this picture depicts this map. Because when n is 1, which is an odd number, you observe that f of 1 will give us 1 minus 1 over 2, which is 0. And when n is 2, I have f of 2, which will be minus 2 over 2. That will give me minus 1. When n is 3, I'll get 3 minus 1 over 2, which will give me 1. And when n is 4, I'll get minus 4 over 2, and this will give me minus 2. So this particular map is the map we are talking about. And I will leave it as exercise for listeners to check that check that this f is 1 to 1 and onto. I've already explained it pictorially, but it's good we'll try it by analytic exercise. And the best way to go is you look at it you consider three cases. Case 1 is taking n1 and n2 in the set of natural numbers. If you take n1 and n2 in the set of natural numbers, consider the first case as the case where n1 and n2 are both odd, but n1 is different from n2. You try to see if you can get an f of n1 is not equal to f of n2. Then the second case is where n1 and n2 are both even, and n1 is not equal to n2. You try to see if you can get an f of n1 is not equal to f of n2. Then finally, you consider the case where n1 is odd and n2 is even, or n1 is even and n2 is odd. Try this case. In that particular case, of course, assuming that they are not equal is no longer necessary, because odd number and even number cannot be equal. So in that case, you try also to see that f of n1 is not equal to f of n2. With this, you conclude that the map is what? Is 1 to 1. Then the next thing is to show that given any integer, there is a natural number, so that f of the natural number will give you the integer. That will establish the fact that f is onto. So this map is actually a 1 to 1 and onto map between the set of natural numbers and the set of integers. So the set of integers is countable. Now, having seen that the set of integers is countable, we all shall agree that the set En is countable for each n, since we've established a 1 to 1 onto map between En and the Z. So now, having done that, what we can now, so since Z, the set of integers, is countable, and then Fn from En to Z is 1 to 1 and onto, then by the explanation I gave above, we have that for any n in the set of natural numbers, En is countable. En is countable. So we've gotten a family, a countable collection of countable sets. So En is countable. Hence, by what we put down at the beginning of this lecture, we can therefore conclude that the union n equals 1 to infinity of En, which is a countable union of countable sets, is a countable set. So this union is a countable set. The next thing I will do is to complete what our target is. Remember our target. Our target is to check that the set of rational numbers is countable. So claim 2. Claim 2 is what I'll handle now. Proof of claim 2. Proof of claim 2. Sorry. I'll put it here. Proof of claim 2. What are we trying to prove in claim 2? We want to show that the union n equals 1 to infinity of En is equal to Q, the set of rational numbers. How do we go about it? Observe that okay, let me first of all recall. Let us first of all recall that Q, the set of rational numbers, is equal to the collection of all P over Q, so that P and Q are integers, but Q is not equal to 0. Recall also that our En is equal to the collection of all M over N, so that sorry, please. Recall also that for any n in the set of natural numbers, En is equal to the collection of all M over N, so that M is in the set of integers. We'll recall this. Now, with this, it is obvious, therefore, that for each n, En is a subset of Q. Because we know that the set of natural numbers is a subset of Z, meaning that this n is an integer. And since n is coming from the set of natural numbers, n is not equal to 0. M is an integer. So this particular thing is of this form, is a quotient of this form. So this means therefore, so we have therefore that for any n I pick in the set of natural numbers, En is a subset of Q, the rationals. And this implies that the union n equals 1 to infinity of En is a subset of Q. So what I've gotten is that, remember that if you are given a subset of a given set, then the union of those subsets must be a subset of the set. The individual sets are subsets. So for that reason, En being a subset of Q means that the union of En will be a subset of Q. Now, the next thing we should do is to show that Q is a subset of the union. Remember, to check that two sets are equal, we must show that the first set is a subset of the second one, and the second one will be a subset of the first one. And if you look at the way I'm going, normally what we do is to check that the two sets are equal. You pick a point in the first one and show that it is in the second one. That establishes that the first one is a subset of the second one. Then the next thing is you pick a point in the second one and establish that it is in the first one. That also establishes that the second one is a subset of the first one. With this done, you can then conclude that the two sets are equal. But in this case, we have a kind of, let me say, semi-trivial situation where, by definition, we can easily see that this particular set is a subset of Q, and that implies that the union is a subset of Q. So the next thing is to show that Q is a subset of this union. What is left to do is, for instance, to pick X in Q and check that that X is in this union. That is easy to do, but because of the fact that we are trying to bring up different methods of seeing the same thing, I would rather do something else that is equivalent to picking X here and showing that X belongs to the union. So what will I do? What I will now do is next, we now show that Q is a subset of union n equals 1 to infinity of En. So if we're able to show this, it means that these two combined will give us that the two are equal. But look at what I'll do now. What I'll do, since we've established that this union is a subset of Q, it means that if this diagram represents, say, Q, if this diagram is Q, the set of rationals, and this portion is the union n equals 1 to infinity of En being a subset, then if I call this portion T, and I'm able to show that this T is empty, it will mean that Q will be equal to this union T, which will mean this union empty. This is En place. This will be this union T. And if T is empty, then I'll get that Q will be this union empty set, which is this, and the quality is established. So that's the approach I'll use. The essence of using this approach is because it may help us somewhere. We are picking elements from here and showing that element belongs here may not give us what we want easily. So let me continue by showing that T is empty. Observe that by this picture I've painted, we can set T to be equal to Q without the union n equals 1 to infinity of En. I want to check that I'm defining T to be this. Remember, this particular notation means the set difference. That is all elements in Q that are not in this union. I want to check it is enough for us to show that T is an empty set. T is empty. Now, let us suppose for contradiction that T is not an empty set. If T is not an empty set, then there exists a point in T. There exists a certain, there exists T not in T. But T not in T, of course, implies that T not is in Q, because T is a subset of Q. And this implies, therefore, that there exists P1, Q1 in, or let me say, P naught, Q naught in the set of integers with Q naught not equal to 0, such that T naught is equal to P naught over Q naught. This is what will happen, since T naught is in Q. So here we have that two cases arise. Two cases arise. Case one is here we assume that Q naught is bigger than 0. Q naught bigger than 0 will imply that Q naught bigger than 0 will imply that Q naught is in the set of natural numbers because it's an integer. And what this would end up doing is this would therefore imply that P naught over Q naught will be element of E Q naught. And this E Q naught, but E Q naught is a subset of the union n equals 1 to infinity of En. Please, this is coming from our definition of En. Remember that En is defined as m over n, so that m is in the set of natural numbers. So if I have that Q naught is a natural number, then M over P naught an integer, P naught over Q naught will be element of the corresponding set of this form, and the corresponding set should be EQ naught. So that is why we have here that P naught over Q naught is in EQ naught. And since we've taken the union of all of them, EQ naught is a subset of the union. Thus, we've gotten that T naught equals, let me say, thus in this case, T naught equals P naught over Q naught belongs to the union n equals 1 to infinity of En. And this already is a contradiction, because by our definition of T is nothing but Q without this union. And by taking T naught in T, it means that T naught cannot be in the union. Now, having made this assumption, and we ended up getting that T naught belongs to the union, what it means is that the intersection of two disjoint sets is no longer empty. And this is a contradiction. So this is a contradiction. This is a contradiction. And that contradiction is coming from the fact that we assume that T is not, the capital T is not empty. Case 2 is the case where we shall assume that Q naught is truly less than 0. Remember, our Q naught, we are having strict inequality here based from the fact that Q naught is not 0. So Q naught can either be bigger than 0 or Q naught is less than 0. So here, if Q naught is less than 0, this will imply that there exists N naught in the set of natural numbers such that Q naught is equal to minus N naught. Because any integer, any negative integer, is minus 1 times a particular natural number. So there is a natural number N naught, so that Q naught is equal to minus N naught. Thus, T naught equals P naught over Q naught will end up being equal to P naught over minus N naught. And this is equal to minus P naught over N naught. And remember that P naught is an integer. Therefore, minus P naught is also an integer. N naught is a natural number. This means that it belongs to En naught. En naught. And again, we have, therefore, T naught, which is equal to minus P naught over N naught, belongs to En naught, which is again a subset of union n equals 1 to infinity of En. And this is another contradiction. A contradiction. A contradiction. Thus, our assumption that the assumption that T is not empty our assumption that T is not empty does not hold. Does not hold. Hence, T is an empty set. And this implies that Q, the set of rational numbers, is equal to the union n equals 1 to infinity of En union T, which is equal to the union n equals 1 to infinity of En, since T is empty. So this shows that Q is the union of this collection of sets. So what have we established? What we've established here is that Q is a countable union of countable sets, and therefore Q is countable. So we've gotten that the set of rational numbers is countable. Let us bear this in mind because this is very, very important. In due course, in the lectures that will follow, we'll try to establish that Q is what we call a dense subset of R. When that is done, it will mean that Q is now, we've seen that Q is a countable set, and if we also establish that Q is dense in R, it means that Q is a countable dense subset of R. And this would therefore mean that R, the set of real numbers, contains what we have a countable dense subset, or has a countable dense subset. And what I'm pointing out here is to mention what we shall meet in future, especially when we do more advanced course in analysis, where the notion of separable spaces will be needed. And in such setting, we say that a space is separable if and only if it has a countable dense subset. So once we establish that Q is dense in the set of real numbers in due course, it will mean that the set of real numbers has a countable dense subset, and therefore R, the set of real numbers, is separable. So the set of real numbers will turn out to be the first separable set we shall meet. I think we've gotten to a point we shall call it a day. Hoping to see you soon. Thank you so much for listening.